So the worksheet problem, right? Basically, hopefully the left circuit kind of looks like this. It doesn't have to be exactly the same. The resistor can kind of move around, right? And the ideally, right, what you want to do is pick your biggest battery and think that, well, the current is going to flow out of the positive end of that battery, right? So we're thinking that, oh, there's going to be some current going to the left, there's going to be some current going to the right, but there's two current, so I better label them, right? Right, and using just Kirchhoff's law, right? Hopefully we can, apply. Let's just do it for the right side, right? The idea is that you want to go around this loop, right? And then just say that, well, the change in voltage, if I start and end at the same point, the change in voltage better stays at 0, right? Because there shouldn't be any change if I start at the same point, end at the same point, right? It's like me hiking to, if I park my car at 5,000 feet elevation, if I did a hike, I came back to the car hopefully didn't move, right? Otherwise someone stole it. Does that ever worry you guys that someone might either tow or steal your car when you're hiking? Yeah, something I think about is like, oh, great, the car is still there. It always surprises me when the car is still there. Anyway, sorry. So let's just do this example real quick, right? Where if I start off, let's say at this point here, let's erase the big circle, right? If I follow the current, the first thing I see is the battery, right? If I see a battery, if I'm going the correct direction along the battery, I should gain EMF amount of voltage, right? And if I keep following this little line here, right, the next thing I run into is this resistor. When I go follow the current through a resistor, right, think about these resistors as little cobblestones and reeds, right, in the river. It slows down the current. So therefore, you actually lose potential when you go across that. And it's just I2 times R2 in this case because of Ohm's law, right? Right, change in voltage across the resistor is I times R. Right, in this case it's just 2 and 2. The next thing we see, if we follow this little track once again, right, we see R3. We're still going in the same direction as the current, right? The current is I2, not I3, right? I see some of you guys make that mistake, right? Because on this entire path, the current is I2, right? And now we end up at the same point, and therefore the potential change has to be 0, right? And then from this point on, that's where you start using your algebra skill and then solve for I2, right? Okay. The next thing I want is to make sure everyone get a little, make sure they're able to do also is that combining Ohm's law, once you figure out what I2 is, I2 I think was it 0.06 amp? That's the right answer, right? Once you figure that out, you can actually figure out what the voltage at this particular point is if we declare this as V equal to 0. Okay? The way you do that is once again, you do Kirchhoff's loop, but you don't get back to the same point. Okay? So if you start off here, right, if we declare this to be 0, we go over this battery, we're going to gain 9 volts, right? Right? So once again, we're going to gain 9 volts. Let's just write in the numbers, right? If we keep following the current, right, we're going to lose I2 times R2 amount of voltage, right? I2 is 0.06 amp, and then R2, you guys remember what R2 was? Was that the 50 ohm, I think? Yeah, that's the 50 ohm, yeah. Okay. And now, right, you are actually at this point. You can actually calculate the voltage at that point, right? Because this is what this is going to be equal to, right? So this is the voltage between the 50 and 100 ohm, right? A lot of times what you will do is you just call it like point A, and then so you can just say, oh, voltage at point A, VA or something like that, okay? So if you calculate this, you should get 6 volts out of this, okay? All right. So now, let's move on to new stuff, okay? Last time we talked about the power dissipated by a resistor, okay? And we didn't get to do this little quick check thing, okay? Where the power coming out of a the power being dissipated by resistor is from this equation in the textbook 28.12. And the reason there's like this long thing of it, right, because power is going to be the current times the change in voltage across that resistor. But then you can combine that with Ohm's law, right? You can plug in delta VR here, right? And then change this equation to I squared times R, or you can change this equation to V squared divided by R, right? Depending on which variable is more convenient to use. So technically, these two are the important ones. These are just side things you can derive by yourself, right? By just substitution. So what we're going to do now is just do a little quick exercise. And let's say we have, well, actually, we don't have to, let's say, standard car battery, at least the combustion type, like the one that burns gasoline, the starter engine runs on a 12-volt battery, okay? And it has an output of 1 kilowatt, right? The K is 1,000, right? 1,000 watts of power. In order to run the starter motor, is that you know, when you turn the engine, it goes and that starts, right? And we're trying to calculate how much current is required to start the car. So we're given, right, the change in voltage. Before we do that, let's just even like draw this, right? So schematically, you can think about the car battery like this, and then the motor, right, is some, you know, something that, you know, makes a turn, right? But we can model this as just a resistor. Okay? Okay. So this basically turns into a resistor with some value R that we don't know, but we do know, right? This EMF is 12 volts, okay? And the power coming out of it is 1,000 watts, okay? Okay. So what we can do is we can use this equation here, right, to figure out, well, the power coming out is going to be the current times delta VR, right? If we want to figure out what the current is, we solve this equation for the current, and this will be power out of that resistor, delta VR, right? The power is 1,000 watts, and then delta VR was 12 volts. If you do this division, you should get about 83. And since this is a current, it should be a unit for amps. Okay. So that's how you use the equation for calculating the amount of power going through a resistor to get the current instead of getting the power. Okay. Right. Part B of this problem, you can even figure out what R is. Okay. How do we figure out what R is? Right. Over here, we have a power equation, right? And then I times delta V, that does not have R in it, right? But we do have a version of it that has R in it, right? In fact, what I'm going to use this one, okay? The reason I don't use the middle one is just because this 83 amp, I rounded that number, right? It's probably going to have more errors in it if I use that number instead. So I'm going to use this version. Let's use the non-green color, right? Power through the resistor is delta VR squared, right, divided by R. So I know what this is. I know what this is, so I can solve this equation for R. So R is just going to be delta V squared over power R, right? And up here we have 12 volts squared, and then down the bottom was 1,000 watts, okay? And then 12 volts is basically 144 divided by 1,000 is going to be 0.144. And since this is a resistance, we know that if we have SI units all over the place, we can trust that it's going to come out in SI units also, which is going to be in ohms. Okay. So that's how you can play around with all these different variables to get one or the other. Okay. All right. And a lot of the homework problem, they're going to give you like different pieces of stuff, and then you have to like solve the equation for the one of the pieces. Okay. There's more examples in the textbook. Highly recommend these examples. You know, as usual, work through it yourself first, right? and then compare it to the book. Okay, don't just look through them, because otherwise you won't take advantage of the full usage of the examples. Let's skip this discussion on power. Next section, we're going to make the circuit more and more complicated to make sure to test you guys on how we can deal with more complex circuits. Okay, so let's say we have a battery, right? This little 4-line thing is the battery, right? And we connect it to a light bulb. Okay, when we a light bulb, in general use, you can model it as a resistor also, as a resistor. Okay. So, but what if instead of connecting one light bulb, we connect 2 light bulbs together? We saw actually in the worksheet, when you connect more resistors together, what does it do to the current? Which one had more current? The one with the loop with 1 resistor, or the loop with 2 resistors? Which one had more current going through it? The one with 1 resistor, right? So it seems like adding more resistance to a path reduces the current, which makes sense, right? Just imagine, instead of 1 set of cobblestones and reeds that's slowing down your current, right? You have 2 sets of them slowing down your current. So at the end, you're going to have a much slower current. Okay. So what we can do is we can model these light bulbs as resistors and apply Ohm's law and Kirchhoff's law to figure out what the amount of what will be the equivalent of these two light bulbs together, right? Let's say they're both identical light bulbs, so each of them will have some resistance R to it. Okay, so I'm going to take this and change it into our model of 2 resistors, right? So this is bulb B, this is bulb C, but they both have a resistance of R to them. Okay, and this is still some EMF. Okay, so if I apply Kirchhoff's loop law, let's say I start off here, right? I start here. The first thing I see is a battery, so I gain EMF amount of voltage. I go over here, I see a resistor modeling a light bulb, right? I lose whatever amount of current, and I made a mistake because I didn't declare the direction of the current. We should always do that. I times R, right? Then we see a second one, we lose another I times R, okay? And that's going to bring us to 0, okay? If you add these 2 terms together, right, we get minus 2 times I times R. I'm going to write it this way. I'm going to put the I in front, times 2R, right? Okay. Compared to this original one, where the Kirchhoff's loop law just tells you that, well, it's EMF I times R, that's going to be equal to 0, right? The difference is that this, the circuit with 1 light bulb, right, has this 1 times R. The circuit with 2 light bulbs has 2 times R, right? So what does that tell you if you put 2 resistors in series? What happens? They add instead, right? So this is different from capacitors, right? Capacitors, when you put them in series, right? These are not capacitors. Capacitors, when you put them in series, they add as reciprocal, right? C equivalent is 1 over C1 plus 1 over C2, right? And then capacitors in parallel, those are the ones that just add simply. Okay. For resistor, it's different, where when they are in series, it's R1, R2, the equivalent, right? This is when they add simply. Okay, oops, I write C's instead. Okay. R1, R equivalent is R1 plus R2. And you can generalize this to kind of dot, dot, dot. Okay? So hopefully that makes sense. Okay? So we just derive, right, the equivalent of a resistor in series is just a simple version of it. So I call this the easy version, right? Because it's easier to just add number versus taking reciprocals and taking reciprocals of the reciprocals, right? So this is different from the capacitor one, right? The capacitor ones, the parallel ones are the easy ones. The resistors, the series ones are the easy ones, okay? With all four combinations, right, you can have resistors in series, resistors in parallel, right? You can have capacitors in series, capacitors in parallel. There's four combinations, right? You just have to memorize one, right? Because once you memorize one, you know the other one, right? Let's say I only memorize that, oh, series resistors is the simple one, right? Then I know the ones in parallel is the more complicated one, right? The complicated one, right, is always going to be, we're going to derive this, right? Parallel resistors, right? It's going to be this 1 over R1, 1 over R2, dot, dot, dot thing, all reciprocal, right? So if I remember that R resistors in series is the simple one, I know the parallel one is the more complicated one, right? The one with the reciprocals, okay? And then capacitors is the exact opposite, right? Right? If I know that resistors in series are the simple one, I know capacitors in series is the complicated one, right? And this is where this comparison comes in, right? Hopefully this is helpful for people trying to memorize instead of memorizing 4 different things, just know one, and then you can figure out the other ones, okay? All right, so let's see if we can just do a little quick check. This time you have mostly you guys do the work. All right, let's say we have a bunch of Christmas lights. We can model the Christmas light as just a bunch of resistors. And each Christmas light has a resistance of 12 ohms, okay? If we string up 10 identical Christmas lights and plug it into a wall jack of 120 volts, what's the equivalent resistance value for this chain of lights, okay? If we connect all these resistors, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then there's a 120 volt power supply here, right? R, 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 all right. What's the equivalent here? You guys think? Okay, so someone already said the 120 ohms, right? And that's because, right, this is 12 plus 12 plus 12 plus 12. You do it 10 times. If you did it 10 times, it's just like multiplying by 10, so you get 120 ohms, okay? So that's okay. So this is kind of a silly example, but it just hopefully demonstrates, okay? Whether you have resistors in series and resistors in parallel, it makes a difference, okay? All right. Before moving on to, actually, I think we'll probably wrap up with this today. There is a little detail about the battery that we need to kind of talk about, okay? The batteries that we've been using in our circuits are what's known as ideal battery, right? In real life, batteries are not ideal because there's actually a limited amount of current that it can produce, right? A 9-volt battery can only produce a certain amount of current before you just basically drain the current too fast for it to work, okay? So the way we model this is by putting in what's known as an internal resistance, okay? And it's gonna say like, wait, how would this help our little how would this make the battery that we're using more realistic instead, okay? So the ideal battery is that what we do is we just change the battery into this little symbol and call it whatever the EMF is, right? If it's a 9-volt battery, we'll have EMF equals exactly 9. If it's a 12-volt battery, it's 12, 120 is 120, right? And it doesn't depend on how much current you're drawing out of it. A more realistic battery, what do? Is we put a internal resistance inside the battery. So we're going to see how does this help, okay? How does this make it more realistic, okay? And we're going to symbolize the internal resistance with this lowercase r, okay? So little r, okay? So, because what happened is that if we follow Kirchhoff's law, right? If we start off here, let's start with the ideal battery. Let's start off here, right? No matter how much current goes out, if we go over this battery, we get plus EMF amount of voltage, right? But if we go over here now with a more realistic battery, okay, if we apply Kirchhoff's law, we're going to gain, right, plus EMF amount of voltage, but we have this internal resistor to deal with, right? Because what's going to happen is that when we go over this resistor, we're going to lose whatever current is coming out of the battery times the internal resistance, okay? So the voltage that the battery actually provides is actually the design EMF when there is no current minus the current that comes out times the internal resistance, okay? So this is a much more realistic version of the battery. Because what happened is that as the amount of current you draw out of a battery goes up, right, it actually drops the change in voltage for the battery, right? Let's do some real numbers. So let's say I have a 9-volt battery, right? And the internal resistance, let's say it's going to be small. Let's say it's going to be 1 ohm, okay? Okay? Right? If I draw 0 amount of current out of it, the delta V across that battery, what is that going to be, do you guys think? 9 volt, right? Because we draw no current, then this term doesn't affect anything. Let's say we draw 1 amp of current out of it. What's going to be the change in voltage across the battery now? Okay, we plug in 9 minus the current is 1, right? The internal resistance is 1, right? We get 8, right? Right? So your 9-volt battery becomes less and less effective as you draw more current out of it. Okay, let's say we draw 3 amps of current out of my 9-volt battery. Right, this is the change in battery, the voltage in the battery. It's going to be 9 minus 3 times 1. That's going to give you 6, right? Right. So basically, the battery becomes less and less effective the more current you're trying to draw out of it. And that's why you can't just power your entire, I can't plug in a 9-volt battery and power this entire building, right? Because it's going to, if I try to draw too much current out of my 9-volt battery, it's going to drop in voltage, okay, until it basically reaches 0. Okay? Okay. So typical internal resistance of battery is going to be 1 to 5 ohms. It's not going to be that big, but it is something you have to consider. All right. So I'm going to do a quick example. Yeah, let's just do it as an example due to time, right? Let's say I have this little circuit here. I'm going to translate this into schematic in a second, right? We want to find the current on the circuit if the EMF is 5 volts with an internal resistance of 5 ohms and the resistor itself is 250. Okay, so let's translate this to a schematic first. What I'm going to do is I'm going to put my battery slightly lower, but then add a tiny resistor here with lowercase r, okay, to model the internal resistance situation, okay? So outside the battery, everything is the same as before, okay? So this thing is just connected to a resistor, okay? We're going to call that big R, and I think this resistor is 250 ohms, okay? And then the EMF is 5, and then the internal resistance is 5 ohms, okay? Now, right, if we want to calculate the current, the first thing I want to do is declare which direction I want the current to go in. I'm going to go from the negative end to the positive end of the battery, right? Applying Kirchhoff's law, I'm going to say, okay, I'm going to start off here at this point, okay? So Kirchhoff's law is going to tell me that, well, the first thing I see is a battery, so I'm going to gain that amount. The second thing I see is actually the resistor, so I'm going to lose I times little r amount of voltage. The second thing I see is actually another resistor, which is bigger, right? And now I'm at the same point, so that's actually going to be 0, okay? Solving for this current, you're going to see that it's going to be E over little r plus big R, right? So this is going to be 5 volts over 5 ohms plus 250 ohms. In other words, 5 divided by 255 ohms. Okay? Okay? And that number should be slightly less than 20. Ooh, who are these people calling me? 5 divided by 255. Of course, it gave me the number, the answer in the fraction. So I get 0.0196 amp. In other words, 19.6 milliamp. Okay, so that's the current I get. So it's going to be this answer. Okay, cut. All right, because without that internal resistance, it's actually going to give you 20 milliamps. So it changes the answer slightly, right? But it's a much more realistic model of a battery. Okay. So that's how we'll end today, and we'll keep talking about other situations and circuits tomorrow.